Kia ora koutou. It's my pleasure to welcome you here to Te Whare Wānanga o Waitaha, the University of Canterbury, in this 150th year of the anniversary of our founding, to our Tauhere UC Connect lecture series. I'm Dr. Michelle Bannister, an astronomer in the School of Physical and Chemical Sciences, Te Kura Matu, and it's my pleasure to welcome you here tonight and to introduce our speaker for the evening. So a few housekeeping things just before we get started. Thank you folks for registering. If you would like to hear more of these lectures in the future, please, there's a little mailing list, just hit that and you'll be able to see a whole lot more of these into the future. They go throughout the year, generally at this time of day, sometime during the week. In terms of where we are in the building, the bathrooms, the toilets, are just out on either side to you here. If you need to leave, there is the doors here. There is also the doors behind you, which will take you out and back down if you prefer. If you hear the fire alarm, we will give you instructions. The evacuation area will be out in that direction, and we will find a spot that is undercover because, yes, you folks have braved the weather to be here tonight, so thank you. In the unlikely, hopefully, event of an earthquake, we will also come and give you instruction how to proceed, take cover, remain in place, and we'll give you further instruction. But hopefully, Rua Moko will stay nice and quiet for us all tonight. All right, last bits of housekeeping. Please, your wonderful digital devices, you're welcome to use them throughout the event, but could you please make them silent at this stage? And lovely, okay, but that is the housekeeping part of this done. So the format tonight will be the speaker will speak to us for about 3/4 of an hour, and then all of your questions are very welcome, please. We'll have microphones here, we can run them up and down if need be, so don't feel you have to shout. I'll handle the Q&A, and in the sense of please put your hand up or whatever, and we'll point to you and then you say your question. I'll repeat it back for the benefit of our wonderful online audience who are joining us via the streaming tonight to make sure everyone can hear it really well, and then our esteemed guest speaker will give their answer. So it's my very great pleasure to welcome here tonight our speaker for the evening. Professor Ray Jayawardhana joins us from the United States. He's come across to be here as part of the Erskine Fellowship Program at Cornell University on the east coast of the United States. He's a professor of astronomy. He's also the Hans Bethe Professor, and he also serves as the Dean of the Harold Tanner Dean of Arts and Sciences. So he's used to wearing very many hats and very many roles. And I have had the pleasure of seeing his work in the exoplanetary community, because I myself work in planetary sciences, so I've seen his work develop across the field of trying to understand the atmospheres of distant worlds. So it's my very great pleasure to welcome him here to speak to you this evening. Professor.
Thanks. Good evening, everybody. I appreciate you braving the weather to be here this evening. And for the next little while, we will look beyond our pressing earthly concerns. And for just a moment, look towards a grander, longer-term quest to make sense of our place in the universe. So welcome. It's easy to forget now that barely a generation ago, we knew of one solar system, with rocky planets on the inside, gas and ice giant worlds on further out, and all but one of the 9 planets orbiting in the same plane. I think a few of you are old enough to remember that. Since then, astronomers have identified a whole host of objects in the outskirts of our solar system. Some of them with their own moons, a few of them nearly the size of Pluto. And that, of course, posed a bit of a quandary. We either had to designate some of these other newly found objects as planets or demote Pluto. And astronomers opted to do the second thing. demoting Pluto to dwarf planet status, which made some people quite unhappy. For a while after, school children wrote letters calling astronomers heartless or worse. Cartoonists had a field day. There was even a protest march in New Mexico where the discoverer of Pluto, Clyde Tombaugh, lived for a long time. Several state houses in the United States passed resolutions declaring that Pluto shall remain a planet. What do these astronomers know? You might think by now we've had time for this dust to settle on the matter of Pluto. But just last year, the New York Times revisited the debate with a lengthy, interactive feature article quoting some who wish to restore Pluto's planethood. All this while, we've continued to explore the worlds in our neighborhood. We've looked for evidence of past water flows on Mars from orbit and from the surface. The Mars 2020 mission with the Perseverance rover has been exploring the red planet now for about 2 years. We've brought back pristine samples of a comet and an asteroid with more on the way. The OSIRIS-REx probe, which picked up bits of an asteroid called Bennu in a dramatic touch-and-go maneuver back in 2020, is on its way back to deliver that sample to the Earth this September. We've investigated icy plumes of Saturn's moon Enceladus, as the Cassini spacecraft, in fact, flew through the plumes of this moon of Saturn. And its discoveries have strengthened the case for subsurface oceans on several moons in the outer solar system. We've caught sunlight glinting off methane seas on Titan, which is Saturn's largest moon. It's a moon with a dense atmosphere rich in nitrogen and methane, and with large liquid reservoirs on its surface, making it in some ways more akin to a terrestrial planet in the inner solar system. We've even captured close-up views of Pluto with the New Horizons spacecraft flying by back in 2015, so that we can marvel at its glaciers and many other splendors rather than lament its identity crisis. The robotic exploration of our solar system continues unabated, with many ongoing and planned missions in the works. The exploration of these worlds, large and small, in our own immediate neighborhood has revealed tremendous diversity of environments and processes. And the discoveries have stretched our imagination in terms of potential habitats for life. As exciting as these discoveries are, I would argue that the greatest revelations of the past few decades have come from beyond the shores of our own planetary system. Namely, astronomers have identified over 5,000 new planets circling other stars since 1995. So after centuries of speculation, decades of failed attempts, there has really been a revolution in the discovery and characterization of planets orbiting other suns. And as you can see here, the pace of discovery has been truly astounding. This revolution has not come easy. I'm not going to show many plots, but this is one. Extreme contrast between a star and a planet means that we can't just point a telescope at a star and expect to see planets in its midst. If you were to look at our own solar system from a nearby star, look at the sun, Jupiter would be nearly 1 billion times fainter than the sun in optical light. 1 billion times. Sorry, the Earth would be about 1 billion times fainter than the sun. Jupiter would be a little bit better, maybe a few 100 million times fainter than the sun. So that means these planets would be lost in the glare of the star if you were to simply point a telescope at a star, just like faint embers next to a bright searchlight seen from miles away. So discovering planets has taken a lot more effort. Nevertheless, in just a few cases, we are not only able to image massive planets around young stars directly using adaptive optics technology on the largest ground-based telescopes, but we are in fact able to take snapshots of these planetary systems so that we can see the motions, the orbits of these planets around those stars over several years. So what you're looking at here is a system of 4 planets, 4 massive planets, super Jupiter planets orbiting a nearby massive young star. This really is a remarkable portrait of a planetary system. I'm going to try to turn the lights off completely for 1 second to see if that would work, just so that you can appreciate how beautiful this image is, the set of images that have been combined to make this little movie. Here's the outermost planet, 2, 3, 4. 4 worlds circling this nearby massive star. So, I'm going to bring the spotlights down and hope that helps. There we go. But for the most part, astronomers have had to be clever and devise other methods to find these planets around nearby stars, such as measuring the wobble of a star when a massive planet circles and tugs on it gravitationally. The subtle shifts of spectral lines towards the blue and the red reveal the presence of a planet in the star's midst. And that's how the very first planet around a normal star beyond our solar system was discovered in 1995 by 2 Swiss astronomers. What you see in the background is a spectrum of the sun with this whole forest of lines due to various elements in the solar atmosphere. And these lines are spectral fingerprints of particular elements. And they always fall on the same set of wavelengths, except when the object is moving towards you or away from you, they shift towards the red and the blue. So you might be used to thinking of the sun as sitting in the center of our solar system with the other planets circling it. But in fact, in particular because of Jupiter's gravitational pull, our sun also wobbles in place. And this is the effect we're looking for when we look at the spectra of other stars and then look for those wobbles that are very periodic that allow us to discover that there must be a planet with that period, that corresponding period in its midst, even if we can't see it directly. Another very highly successful method for detecting planets involves measuring periodic dimming of stars when a planet passes in front. Just like Mercury here and Venus sometimes are seen to pass in front of our own sun. What you're looking at here is the planet Mercury transiting the sun, which happens every once in a while. So does Venus transit the sun. But if you're looking at another star, you don't see the star like a nice big plate in the sky. You see a dot of light. So with exosolar planets, what you notice is that the brightness of a star dims for just a few hours while something is blocking a little bit of its light. And that dimming is minuscule. For a planet about the size of Jupiter passing in front of the sun, that dimming is about 1%. For a planet about the size of the Earth passing in front of our sun would dim the sun by about 1 part in 10,000. So imagine how difficult that is to measure. And yet, that's exactly what astronomers are doing. With ground-based arrays of telescopes like this one, that's a transit of a transiting planet, you can actually detect planets this way. Now, of course, planets that go around like this, you'll never see. Only those that happen to transit, whose orbits are lined up such that they are going to pass nearly edge-on, are the ones that you will discover. But by monitoring thousands of stars at once, it's possible to discover planets through the transit method. The floodgates really opened for this technique when a space telescope called Kepler was launched in 2009. For several years, this telescope stared at a little patch of the sky about the size of my palm at arm's length, that little patch of the sky. And it monitored nearly continuously the brightness of about 150,000 stars in search of transiting planets. And it was successful, highly successful. In fact, the Kepler Space Telescope found about over 2,600 exoplanets. About half of all exoplanets we know today were discovered by this one small space telescope. And the diversity of worlds and planetary systems that Kepler discovered is truly remarkable. This is an animation showing 726 multi-planet systems. So systems with more than one planet orbiting the same star, how their orbits work. This is a nice, animation made by astronomer Dan Fabricki at the University of Chicago. I find this mesmerizing. You can just kind of stare at it and think about all the patterns that your eye catches. There it is zooming in to a subset of those planetary systems. You can see some of these planets are incredibly close to their stars, circling them every few days. Some of them 1.8 Earth days. So a whole year on that planet would be 1.8 Earth days. Some of the others are a little bit farther out, and there's different sizes, different motions, different speeds in their orbital motions. Quite a remarkable diversity of solar systems out there. And this is just 726 of them. The Milky Way galaxy is home to hundreds of billions of stars and potentially hundreds of billions of planetary systems. There's a lot of follow-up work we can do with transiting planets. For example, by timing those transits very, very precisely, we can tell if a planet's orbit is changing. Because if it's a very steady orbit, it should be very, very steady. It should come back to the midpoint of a transit exactly at the same amount of time every time. But if there are additional planets in the system tugging on that planet, its orbit may sometimes speed up and sometimes slow down. So the transit happens a little too soon or a little too late, and then you know something else is going on. Either there's another planet that is not transiting, that's tugging on the inner planet that is transiting, or maybe the inner planet is spiraling into its star or doing something odd. And as one example, just a couple of years ago, with two of my postdocs, we looked at data from NASA's TESS mission, and we timed very precisely the transits, many transits of this one hot Jupiter planet, and we confirmed that, in fact, its orbit is shrinking. And ultimately, in about 3 million years, this planet will fall into the star. 3 million years is a pretty short time as cosmic time goes. And the reason it's doing that, we think, is that the planet is close enough to the star, it's racing tides on the star, like the moon races tides in the Earth's oceans. And it's losing some of its orbital energy, and therefore, as the energy is dissipated, the orbit is shrinking. At least in some cases, especially those close-in big planets, we can also learn about their atmosphere and climate by tracing the changing phases of a planet as different parts of it are illuminated as it goes around its star. Just like the phases of the moon, different pieces of the moon are illuminated by the sun, we can see different phases of a planet. And this is a technique we used, in fact, using Kepler data several years ago. Lisa Esteves, who was a PhD student in my group at the time, we used Kepler data to find that two of the hottest planets we were looking at had evidence of hotspots in its evening side. There was a clear hot evenings on that planet. And then 4 others that were a little bit cooler had evidence of cloudy mornings. Imagine starting to learn something about planets that are hundreds of light years away using data from these telescopes near the Earth. And in the case of transiting planets around bright stars, we can learn even more through remote sensing of their atmospheres. So when the New Horizons spacecraft that I mentioned passed by Pluto, at some point it looked back at the sun behind Pluto. So this is sunlight streaming through Pluto's atmosphere. And with this beautiful picture, basically you could study the hazers in the atmosphere of Pluto in our own solar system. But we could do the same thing with these transiting planets, because you've got a star lighting up a planet. A little bit of that starlight is blocked by the planet, but some of it streams through the upper layers of the planet's atmosphere to our telescopes. That means whatever is in the atmosphere of the planet might leave imprints on the stellar spectrum that we can measure. And that way we can learn something about the atmosphere of the planet, even though we can't take a direct picture of it. And these spectral fingerprints tell us what is in the atmosphere of the planet, the constituent species. But also we can learn something about the temperatures and pressures in the atmospheres of these worlds. So far, a handful of these planets have been looked at with telescopes like the Hubble Space Telescope, the Spitzer Space Telescope, and also large telescopes on the ground. And astronomers have been able to see spectral fingerprints of things like water, methane, sodium, potassium in the atmospheres of some of these worlds. And in some cases, able to infer that they are cloudy atmospheres. So we're beginning to do these kinds of things, and that's the kind of work that my research group at Cornell is focusing on. We're very active in characterizing alien worlds through spectroscopy. In particular, we use what are called high-resolution spectrographs on large telescopes around the world, in particular telescopes like these in Chile, Hawaii, and the Canary Islands. We use infrared and optical high-resolution spectrographs to characterize exoplanets. As one example, a couple of years ago, another PhD student in my group, Emily Diebert, led a paper in which we reported detections of ionized calcium and sodium on a planet that is so hot that iron gets vaporized on its day side. These planets are so close to its hot star that the temperatures are so high as to vaporize iron. More than that, from the profile, the shape of the calcium lines in the spectrum, we could suggest that there might be strong winds in the planet's upper atmosphere. So even though I do this for a living, I still find it remarkable that with today's telescopes and instruments, we can already learn so much about the atmospheres, their constituents, their physical properties, the presence or absence of clouds, and even sometimes hints of large-scale wind patterns on planets that are orbiting stars hundreds of light years away. Isn't that mind-blowing? This is not theory, this is not speculation, this is not a thought, this is measurement, right? It's quite remarkable that we can make such precise measurements as to begin to learn something about the physical nature, characteristics, climate of these alien worlds. So dozens of media outlets reported on Emily's findings a couple of years ago about this hellish world. The idea of sort of iron vaporizing drew a lot of headlines and attention, as you might imagine. We just submitted actually a follow-up paper on that same planet doing a much more comprehensive analysis of our data, and we recovered strong signals of iron, calcium, and sodium, as well as tentative detections of several other atomic species in its atmosphere. So these results are part of an ongoing 3-year large observing program using the Gemini telescope, which is an 8-meter telescope on Mauna Kea in Hawaii. And our program is to get spectra, high-resolution spectra, of several dozen exoplanets spanning a range of temperatures and masses. Here you have the planetary temperatures, planetary mass, and the colors correspond to different temperatures from the hottest to the coolest. And of course, these are the big hot planets. These are the small cooler planets. And of course, the cooler planets, the smaller planets, are a lot harder to study because their signals are smaller and harder for us to discern. And that's where the James Webb Space Telescope can help. I was very excited and a tad nervous as we watched the launch online on the Christmas morning of 2021 with my kids. I've been part of a team by that point for 16 years that developed one of the 4 instruments, the smallest one led by the Canadian Space Agency, for James Webb. So the stakes were high, to say the least. After all these years of work and anticipation, it was quite something to see the telescope actually in space. This is a photo taken soon after it separated from the launch vehicle. James Webb orbits the sun, not the Earth, 1 million miles from here. So unlike with Hubble, which is in low Earth orbit, there is no chance of repairs or upgrades in the coming years. So luckily, so far, Everything's gone very well, and it's gathering incredible data on cosmic denizens near and far. So our nearest instrument team, for all the work that we put into it over almost 2 decades, we were granted 400 hours of guaranteed observing time with James Webb. And we're dedicating half of that time, about 200 hours, to look at the most distant things in the universe, the earliest, farthest galaxies during, we think, would be the time of cosmic dawn. And the other half of the time, about 200 hours, the other 200 hours, we're dedicating to look at exoplanets, to characterize a sample of exoplanets, including a few that are not much bigger than the Earth around the nearest red dwarf stars. This nearest instrument provides spectral resolution of about 700, which is much, much lower than the ground-based high-resolution spectrographs that we've been using with the big telescopes in Hawaii and Chile. But of course, James Webb wins hands down when it comes to sensitivity. By being in space, by operating in the infrared, it's really able to reach sensitivities that we just couldn't from the ground. So there's a lot of excitement around what's about to be revealed. In fact, the very early results from James Webb are already out. Here you can see the nearest spectrum of a hot Saturn-type planet called WASP 39b that revealed evidence of water, potassium, as well as indications of clouds in the atmosphere of this world. The precision and the broad wavelength coverage of nearest on James Webb allowed the authors of this paper to investigate very specific things like the ratio of carbon to oxygen in the atmosphere of this planet. They were able to put some constraints on how enriched in heavy elements the planet's atmosphere is compared to our sun, compared to its own star. That is starting to get pretty specific. You're learning, getting at the kind of detail that is hard to believe because it's really not in our solar system. Remember, these are planets around other stars so far away. And such measurements could begin to give us a sense of how such planets formed and evolved. The evolutionary history of the world might be deduced from the measurements of various elemental abundances and ratios in particular. So in our own guaranteed time program, we are targeting planets with a range of properties, as you might expect. You want to sample a whole range of planets to get a sense of their diversity. We are sampling planets of different temperatures, masses, radii, some that have indications, prior indications of being cloudy or being clear, others that have indications of temperature inversions in their atmospheres. So these are the 14 targets of our guaranteed time program. Here are some of the known extrasolar planets. These are some of the more massive ones. This is in terms of Earth mass. These are rocky, small Earth terrestrial worlds. You can see we have a few down here. We have sort of Uranus, Neptune type planets. We have sort of ice giant planets there. And then these are super Earths. These are ice giants. And then we have some very hot Jupiter gas giant planets out up there. So we are trying to sample this whole range of planets to the extent we can, given a limited amount of time. 200 hours seems like a lot. We can only fit in observations of a little over a dozen planets in that time. So the good news is already 5 of our guaranteed time targets have been observed. And there are graduate students in different parts of the country, in the world, with their hands on these data, really excited to get what we can out of the very early observations of exoplanets used as part of our guaranteed time program. So one of the targets, one of the more interesting ones, is a star called TRAPPIST-1. It's a nearby red dwarf star that hosts a remarkable system of 7 transiting planets. 7 transiting planets around one star. We can see each of the 7 transiting in its own orbit and its different orbital periods. A few of these planets are in an interesting place. E, F, and G, not very imaginative, I admit. These planets are kind of in a region that we call the nominal habitable zone. So F in particular is right in the middle of it. E might be on the inner edge, G is sort of close to the outer edge. For this particular star, because it's a red dwarf, the habitable zone is much smaller than it is in the case of the solar system. The entire TRAPPIST system would fit right in there, well inside the orbit of Mercury in our solar system, right? Because the star is so much less luminous than the sun, the planets out here are heated to the same temperatures as the Earth over here, which is right in the middle of the habitable zone in our own solar system. So it's a sort of a shrunk down miniature version of a planetary system with 1, maybe 3 habitable planets. By habitable here, all we mean is that they should have the right distance from their star to have the sort of temperature that would sustain liquid water on the surface. What we do already know from observations made so far is that these planets are likely to be rocky, not gaseous, because we have inference of their densities, their bulk density. What we don't know for sure is whether they have measurable atmospheres worth talking about. So that's where the James Webb Space Telescope comes in. The planet F in particular is right in the thick of that habitable zone. There's a lot of excitement about what kind of planet it might be. So we expect James Webb to provide the first real detections of terrestrial planets that are rocky, planets that are approximately in the habitable zone of their star. Of course, whether a planet is in fact habitable or not depends on many crucial factors, like the composition of its atmosphere, whether it has volcanoes, oceans, plate tectonics. So all sorts of things that's really more sort of geology, planetary science, a little less astronomy. But they really come into play. That's why the Earth is habitable. Without its atmosphere, without some degree of greenhouse effect, the Earth would be way too cold for life as we know it. So you do need these other factors, not just the right distance from the star, for a planet to be truly habitable. Even despite its incredible capabilities, we don't expect that James Webb is able to look for direct evidence of life, what we call biomarkers or biosignatures. That's likely to take a special purpose space telescope built for that purpose rather than a general purpose observatory like James Webb. One could get lucky, of course, but that's not likely to be within our realm of ability in the coming months and years. So what you're looking at here is actually a spectrum of the Earth, which we do know to be inhabited. And the way this spectrum has been taken is by taking a spectrum of Earthshine of the moon. So the reason even when you see a crescent moon, the rest of the moon isn't completely dark, and something that Da Vinci figured out a few centuries ago, was that sunlight reflecting off the Earth falls on this part of the moon, making it not completely dark. So by taking a spectrum of this part of the moon, you could basically get a reflected spectrum of Earthshine. And that's what this is. And if you look at this, you can identify things like ozone, oxygen, water, lots of water, carbon dioxide, methane, spectral features due to fairly common molecules in the Earth's atmosphere that we tend to associate with life at one level or another. Now, the detection of any one of these, whether even if, for example, water, which we have detected in exoplanets, except in exoplanets that are gas giants and extremely hot, not likely to be habitable. So the detection of any one of these, maybe even two of these, doesn't necessarily constitute strong evidence of life. But if you were able to detect multiple of these so-called biosignatures coexisting, maybe that would give you a sense that some confidence that the planet might be inhabited. So spectral fingerprints of molecules like oxygen, ozone, water, carbon monoxide, carbon dioxide, methane. The hope is that someday we will be able to take a similar spectrum, perhaps a slightly cruder version of that, not as high signal to noise, of an Earth twin around another star in its habitable zone, and we might see some of this appearing. But even if we weren't able to do that, if we do detect these so-called biosignatures, that still doesn't tell us whether we're looking at slime or civilization. Right? It's life either way, but you might care more about one than the other. Unless we can also detect artificial radio signals coming from that same planet. Then things would get interesting, right? So if you were to find a planet with spectral fingerprints of biosignatures, the way I'm describing this quest going along, you could, of course, turn your radio telescopes at that same world and look for any evidence of artificial signals. How would we react if we were to find compelling evidence of life elsewhere? My sense is that spectral fingerprints may be a one-week news story. Radio signals, on the other hand, would likely be much more dramatic, because we would know that a messenger exists at the other end, even if we can't understand the message. You don't need to decode the message to know somebody is sending it, as long as you can be confident it's not of natural origin. It's not a natural physical process that's producing the signal. Then you would have found life elsewhere with the technology to send that signal. Even if you don't know what it says, right? That's sort of secondary. So we really are going through an exciting, interesting time in this story, and we really are witnessing a truly extraordinary era of discovery. Not only are we finding alien worlds by the thousands, but we're able to do remote sensing across hundreds of light years to measure the characteristics of a subset of them. So I think it's not an exaggeration to say that this moment in history is comparable to when Galileo first turned his telescope at the heavens 400 years ago. And in particular, when he discovered those 4 big moons of Jupiter, and by tracing their positions night after night, he could show people that these objects are revolving around Jupiter. In other words, not everything in the universe is revolving around the Earth, and here's direct evidence of it. I think these exoplanet discoveries are beginning to provide the completion of that Copernican revolution. They're really beginning to tell us how we stack up in the cosmic context. They're beginning to give us a true measure of our place in the universe. So stay tuned. Thank you. I think we have plenty of time for questions.
We have plenty of time for questions. So to remind everyone, we have microphones, which thank you very much to our wonderful UC volunteers. Microphones will come to you, and if you could please state your question. Your question is a question. A statement is a lovely thing, but give us a sentence that's a question, and then that'll be come through the microphone so for the benefit of our online folks. So just make sure you're speaking well into the microphone. Thank you. All right, please, here's questions. One down the front here.
The United States government have announced recently that they keep on spotting UFOs. Have you considered looking where they are finding these things to perhaps find life from somewhere else that's very close by?
UFOs are UFOs, as in they're unidentified, right? So just because you can't definitively identify something doesn't necessarily mean it's alien. And given the kind of distances we're talking about between stars, the interstellar space is so vast that that the idea that somebody would send a probe that sort of barely kind of appears to a few people and not the rest of us is incredibly unlikely, right? I mean, if you have the technology to send probes across hundreds of light years, and by the way, I think we really forget that the fastest spacecraft we've ever launched travel at a tiny, tiny fraction of 1% of the speed of light, right? So the kind of technology that you need to crisscross hundreds or thousands of light years is sort of almost unimaginable to us. That doesn't mean it's not impossible, but it's so advanced that you would think that kind of technology would be relatively easy to recognize if it was near the Earth or on the Earth, on the ground, right? So it's unlikely. I mean, more and more of these previously described UFO sightings that were previously described as UFOs are turning out to be high-altitude balloons and military aircraft and all sorts of things, right? I mean, the number of people who report Venus as a UFO, you'd be surprised by, like year after year after year, because there's this really bright thing that shows up. And then astronomers like Michelle get a call, as, what was that thing in the sky at this time and this place? It's easy to kind of not know something, but just because you don't know that, the aliens should be sort of the last resort, not the first. So that's not really helping us at this moment with this particular quest. Now, you do raise an interesting question, which is when we're looking for biosignatures, I talked about looking for evidence of life, whether it's slime or civilization, but we could also there are scientists who are thinking about how to search for technosignatures, right? Rather than biological or chemical signatures, what about a really advanced civilization may have our civilization has been leaking radio waves for close to 100 years into space. So a much more advanced civilization could have technosignatures that are easier to detect from farther away. So there are SETI scientists, the Search for Extraterrestrial Intelligence type scientists, that are kind of using radio telescopes, infrared detectors, all sorts of things to look for technosignatures. And that would be very interesting. Yes?
You talked about... Hello?
Yeah.
You talked about taking spectra of a couple of planets in the TRAPPIST-1 system. I know there's a little bit of debate about TRAPPIST-1 being quite a volatile star because it's a red dwarf. Have you ever done any spectroscopy around the same planet around a volatile star multiple times to see how the atmosphere changes?
That's a great question. So the question has to do with the fact that in terms of habitability, it helps to live next to a relatively well-behaved, quiescent star. And our sun happens to be a middle-aged, well-behaved star for the most part. That doesn't mean it's sort of perfectly quiet, right? But some of these red dwarf stars tend to be more active, and young stars tend to be active. The sun very likely was much more active in its youth than it is today. So there's a concern that even if you had the right conditions in terms of a rocky planet with a rocky surface and a good, decent atmosphere, that the activity of the star could kill off life or the potential for it. So that is the concern with these red dwarf stars. They offer us a technical advantage that it's easier to, the contrast between the star and the planet is not as bad as if it were between a star like the sun and a planet like the Earth. So it gives you an advantage in terms of detectability, but on the other hand, whether these environments are not so amenable to life or dangerous, we don't really know. It is also a challenge when we do spectroscopy of some of these transiting planets, and we do see evidence of stellar activity in some cases, actually confuses our planetary signal as well sometimes in terms of detectability. So one of my postdocs is very interested in figuring out how to take out the stellar activity out of the spectrum so we can get a cleaner signal of what's coming from the planet separately from it. So it's a great question. We don't know. It's one of the beauty of science is it's a quest. We're asking questions we don't know the answer to. We don't know it ahead of time. And also the other thing is that TRAPPIST-1 is one system, right? I mean, really, if you're looking for life or evidence of life or habitable planets, you really should be looking at lots and lots of them, not a single one. But we had to start somewhere. So I think that, I think it's an exciting time. I'm not sure that we will have a definitive answer. And one of the things that people often ask me about, do you really believe there's lots of life out there in the universe? I think the odds are yes, because our one Milky Way galaxy alone has a couple of 100 billion stars. And the data from Kepler showed us that planets are rather common, planetary systems are rather common. So there must be hundreds of billions of planetary systems just in one galaxy. So the idea that life only originated and survived on one planet seems preposterous. Now that doesn't mean, I think part of the beauty of the science is that you don't know the answer, which means it may be that after decades of searching, it'll turn out that we are sort of alone in our neighborhood. And our neighborhood is a small place, right? It's sort of tens, maybe hundreds of light years or 1,000 light years from us. Maybe there is life, but maybe no advanced technological life. That's quite possible. I mean, we only know of one biology, and we can only generalize so far from one example. And often when you generalize too much from one single example, you turn out to be wrong, right? So with exoplanets, we found such a diverse range of planets and planetary systems that we couldn't have predicted just from looking at the one solar system we knew about beforehand. So similarly, we need to keep an open mind. And I think either way, it's quite fascinating. Whether we discover evidence of life elsewhere in the coming years or decade, that could be a momentous occasion for human history. It may not feel like it, as I was alluding towards the end, that tomorrow you wake up and all of your worldviews have changed. Probably not. But I do think that over generations and centuries, it could be the kind of turning point like Darwin, like Galileo. Like that kind of momentous change in the human humanity as a whole over time. Maybe not overnight. There were some questions up there.
One down here first, and then
That one first.
Oh, yeah.
Okay, up to Bethe first.
We good? Yeah. You mentioned a specialised telescope in the wings, I suppose, for looking at biosignatures on planets. What would the nature of that, design-wise, compared to, say, the James Webb or the Hubble? What would be its design characteristics?
Yes, so the question is about what kind of a specialized telescope might allow you to look for biosignatures, take spectra that have of a terrestrial world with the possibility of detecting biosignatures. So the challenge is again to do with the contrast, the brightness contrast between the star and the planet, which means for most telescopes, we have great optics, but for this you really need incredibly precise optical surfaces. So there's no scattered light or as little scattered light as possible. If you're looking for a signal of like 1 part in a few hundred million or a million, 100 million, you really need to control the path of light through the telescope to the instrument incredibly well. So there are a couple of ideas. One is a coronagraphic type of telescope that would sort of suppress starlight, but also can have incredibly good optics that allow you to get at the planetary signature. Another one, and one of those designs that have been proposed is actually called is called a sunshade, where there might be a free-flying spacecraft in front of the telescope blocking the starlight. And another one is sort of a combination of telescopes, what's called an interferometer in space, that might use the wave nature of light to cancel out light from the star, but look for things right next to it very precisely. So there are definitely designs. There are even laboratory tests of some of these sort of techniques that are being carried out. So the technology is sort of getting close to being within reach. It's not quite there, but it's not that far away. So that's an exciting thing. The other thing also, the flip side of it is also the science, which is it would be nice to be able to narrow down the best dozen targets towards which you want to point such a telescope, right? So you can maybe even purpose design it. So for example, there are people thinking about very, very particular design to try to image the planet around Proxima Centauri, right? That's a very, you can make it just so that you can do that one. May not, so there's a lot, you can fine tune it to that much. Maybe that's not the best bet you want to make, but you want to have at least a dozen, maybe dozens of targets that you can go after. That would be exciting. Yeah.
Kia ora, tēnā koe, te takata, te matatau, ko tēnei pātai. It's about something I saw in about 2012 on YouTube. Can you hear me? I've got a quiet voice.
Yeah, I can hear it.
It had to do with this enormously long, radio receptor. And I don't know, it's just something I watched, and I've never remembered what this thing was called. But someone who was observing on that occasion noted that there was a communication, so it's one of them in your slide. Do you know anything about that? Do you remember it?
Yeah, it's very hard based on your very vague description to figure out what you mean. There was something that was noted on a notebook from a radio observer at some point called the wow signal. it was called just the WOW, the wow signal.
Oh, yeah.
But it doesn't, it was a one-off.
That's what
Any
they said.
follow-up had not detected anything, so it's very hard to tell.
What was the instrument called?
I don't remember
Oh,
specifically
sorry.
right now, but it was one of the radio telescopes. But that was decades ago now.
Was it decades?
Yeah.
I saw it about 2012.
Yeah, you might have seen it now, but I mean, it was the wow signal has been in the literature for a long time.
Thank you.
Yeah, if that's what you're referring to, I'm not sure. But, yeah. Okay, sure. I think yeah. Go ahead.
Hello?
Yeah.
Hi. So Stephen Hawking spoke about how he was quite concerned that we are sending so many radio waves and we sent a map off on Voyager to our location.
Yeah.
I was wondering if you sort of agree with that assessment that that's worrying to advertise our presence here?
I don't. So the question is, do we worry about advertising our location in case the aliens find us? Sort of the least of my worries, I would say, with all due respect to Stephen Hawking. The radio, the signals that have leaked from the Earth, they're pretty weak. They're probably, tens, maybe 100 light years away at this point. I think the odds of the Voyager plaque being, it was more like a message to ourselves than to somebody else. It's much less likely to be detected than it is for us to think about what might one say on behalf of all of humanity. It was an interesting intellectual, cultural exercise. I don't think that without knowing where to point a signal, it may not be the most productive use of time to kind of keep sending specific signals. We could send it to a cluster of stars and hope one of them has a planet with detectors. Again, given the interstellar distances involved, I really don't think there's a lot of danger of that. I worry a lot more about sort of what we might do to our own planet than what somebody else might do to us from outside.
I got two questions. One is about morality. The other one is about epistemology.
So we'll take one question, please, and then we can come back to you if we have another chance.
Yeah, the morality one is close to the last question. Would you imagine the possible types of morality that the alien could hold? Because if we expose our presence, would they, due to the competition of energy or resource, will they annihilate us?
I have no idea what kind of morality another alien species would have. Again, we're not competing for resources of the same sun, right? If it's not in our solar system. So there's no kind of question of competing for resources in a big, vast universe where we aren't able to tap into all of the resources of our own sun. So we're not worried about, the resources for another system or another star. So it seems kind of far-fetched to me.
Okay, my second question is about the...
We'll come back to you when we have a chance. So we have another question. One over here and then one down front. We can come back.
Is this on? Given that we detect the detection methods used for finding exoplanets mostly favour large planets, do you think there's detection bias in the way that we find exoplanets? We find considerably more large exoplanets than small rocky exoplanets?
Oh, the question of detection bias. Indeed, it's easier to find bigger planets closer in orbits. So there's certainly biases, observational biases. We are aware of it. So in terms of do we know the entire diversity of planetary systems? We don't. But because Kepler stared at 150,000 stars, within about 1 astronomical unit of a star, we have a pretty good census of inner planets because, out of 2,600 that Kepler found, planets that Kepler found, and hundreds of multi-planet systems, we have a pretty good sense of the frequency of planets in inner solar systems. We have very little idea of planets that are, 30, 40 times the distance from the Earth, except through this whole another technique called microlensing. So that provides some data for the farther out planets, right? So we do have gaps between the different techniques that we're not as sensitive to. in terms of mass ratios and orbital distances and things like that. So there are definitely, we are not claiming that we found every, the full census of potential planetary architectures or anything like it, or that we've sampled it very well. But the ones we're finding are interesting, are already pretty remarkably diverse, that they've sort of opened up our eyes to a much greater range of possibility than our own solar system did.
What do you think of the possibility of microbial life, especially on the icy moons of the outer planets?
Yeah, so the question is the possibility of microbial life. I mean, as I was sort of speculating in this case, it may be that sort of primitive or microbial life is relatively common in the universe, but complex, advanced technological life may not be. I mean, that's one of the possible, realities out there, right? And we just don't know the answer, but I think, on Earth, it seems like the evidence is that life originated relatively soon after it could originate. As the conditions got just good enough, life seemed to have somehow originated. And the other thing is we've also got, by now what we have in broad brush terms is that we do find planets are common. We think that planets with inhabitable zones seem to be common. We also find the ingredients for life are very, very common in the universe. In interstellar clouds, we're detecting relatively complex molecules. So, in meteorites, we're finding evidence of complex organic molecules. So the ingredients are there, the habitats are there, but we don't actually have definitive detections of life, so we're yet to get the answer. But it seems to me that, if you were to take a bet, you would bet that microbial life would be relatively common. Whether there's microbial life in our own solar system, in the subsurface oceans of some of the moons in the outer solar system, we don't know. But there's certainly a lot of interest in figuring that out. Because there are interesting conditions in which life could evolve that are a little bit different from the Earth today, but may have been not so different from the early Earth, perhaps. So that would be very interesting to find out as well.
A quick question just about, for instance, so planets, exoplanets, how common is it to find an exoplanet that's on like an unstable orbit that's, say, spiraling into the sun?
Yes, great question. It's not often we find a planet in an unstable orbit because, that you could argue is a selection effect. They could have spiraled in a short time. So if they were to be doing that, so if they weren't in a stable orbit, they wouldn't be sitting around for billions of years for us to come and find them, right? So there's only evidence of maybe 2 or 3. There's reasonably good evidence of orbital decay, but not many. Yeah. It doesn't mean that a lot of them may have fallen into their stars early, pretty rapidly soon after they formed, for example, and we wouldn't be seeing them in the process of falling in.
Yeah, have you spotted any exomoons yet?
Great question. People have been looking. It's a bit puzzling at some level, but rings and moons of exoplanets are things that maybe through the transiting method you might be able to detect. And there are people who sort of develop the algorithms to run through the data to look for them, and so far no definitive detections. Yeah. Lots of hands up still, okay.
Yeah.
Okay.
Hello. How serious a problem is the profusion of satellites around our Earth to your observations?
Maybe Michelle should answer that question.
We actually do a bunch of research on that here at the University of Canterbury, and we are seeing the sky density of satellites definitely start to pick up in the skies above New Zealand. We know it's going to be an issue for observatories like the big Rubin Observatory under construction in Chile, which starts observation in 2 years. So that's going to survey the whole southern sky every 3 nights. So we expect that to be substantially having to try and work around the satellites. For exoplanet spectra in particular, it's a little less of a problem at the moment.
Because we're looking at a tiny little field of view of the chance of a satellite crossing that tiny at the 7 hours I'm observing, not so high. But for all sky surveys, looking for Kuiper belt objects in the outer solar system, other kinds of science, it is a problem. It's a growing problem.
Just back to our solar system, say life or signs of life or unmistakable signature of life is found on Mars or a moon of Jupiter or Saturn. So I guess it just shifts the question to where was it self-seeded or individually seeded, if you see what I mean? Did it develop individually or seeded? So then we're still stuck in the solar system. Are we alone or not? How do you think it would change if life was found on Mars or signs of life found on Mars or the moons?
Yeah, it's a great question. Is the question if you were to find life on Mars or evidence of past life on Mars or one of the moons of in the outer solar system, presumably by doing genetic analysis, you could tell if it's part of the same tree of life as life on Earth or not, and that would kind of answer the question of is there a connection or this independent origins, right? I mean, the independent origins would be really interesting because if it can happen twice, all of a sudden you're like, well, it could happen 1,000 times. Why not, right? There's a big difference between 1 and 2, right? In terms of thinking about the likelihood of life originating easily or not. So that would be particularly interesting. But if it is sort of seeded across planets within a solar system, that could be interesting as well. But perhaps wouldn't tell us quite as much about what might happen on the other side of the galaxy, right? So.
Thank you. I think we're going to have to conclude the question time there because we've just come up to the hour.
I guess so. That's where the lights went up. So tell us it's time.
For the many varied and wonderful questions, and we possibly may be able to ask the professor a little later, but if he is staying around to touch. But please join me in thanking Professor Jayawardhana for